let me just pull something up. I don't know if you remember this, but we wrote down an expression for the intensity, which is the average energy in 1 second per unit cross-sectional area delivered by the wave. It was, if I remember correctly, usually I remember this is the amplitude squared times epsilon c over 2. Let me just double check. That's the intensity. It's the average energy delivered in 1 second per unit cross-sectional area of the electromagnetic wave. Let me just, that's a derivation that I did on the board, so chapter 32. And this is at the end of the chapter, if I remember correctly. There it is. Okay, yeah, so I did remember it correctly. So this C is the speed of light in vacuum. Epsilon naught is called the electric permittivity of free space. It's just a constant associated with vacuum. The 2 downstairs, and then this is the amplitude. Remember that this 2 came from taking the average of the cosine squared. Right? So of the cosine square or the sine square of a wave, when you take the average of the cosine square of an angle or the average of a sine square of an angle, you pick up a value, you get an 1/2. And that's where this 2 came from. So this is a way of writing down the intensity of the wave, right? And this is the amplitude. Let's just call it E sub 0. I think it's called in my other notes over there in the other chapter. Let's say the amplitude, let's just call it E sub 0. In other words, it's like the electric field is equal to the E sub 0 cosine, for example, of kx minus omega t, something like that. And if you like, this is, polarized along the y-axis. But then when the intensity is proportional to the square of this electric field, so it'll square that, but then you'll have to take the average of the cosine square, which gives you the 1/2. And then, pick up those factors. So that's a calculation that I did back in chapter 32. And now, in this topic of, in chapter 33, with the polarizers, what does Malus's law say? Well, the very first result is this. What if I have unpolarized light coming in? The electric field is randomly polarized, right? Unpolarized light. And then I send it through a polarizer, and let's say that the transmission axis of this polarizer is vertical. Or actually, it's the blue at an angle over here. So I'm gonna imagine this light is coming at me. So I'm gonna draw it like this. The electric field is up, down, right, left, this way, this way, this way, this way, randomly polarized with an amplitude E naught. Okay? It's like this is oscillating boom, 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 boom. This one is boom, 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 boom. This one like that, this one like that, right? It's just oscillating like that. Now, what if I place a polarizer like this and the transmission axis is like, it doesn't really matter. Let's say the transmission axis is vertical. So T means the transmission axis. That means that the electric field components that are parallel to that axis are going to go through. So in general, right, so what is the intensity of this light over here? The intensity would be what? It would just be that expression, right? Epsilon naught C over 2 times the electric field squared, right? Okay, so, and then what happens is I can think of this electric fields over here, just like one of them, let's say like this. And it makes an angle theta with the transmission axis. So when the light goes through this polarizer over here, what will it look like? Well, only I can think of this electric field as having 2 components. This one is the one that's going to get transmitted, E naught cosine of theta. And the other component of the electric field, E naught sine theta, will get absorbed. So what would you get on the other side of the polarizer? you're just gonna get an electric field it's only the component, right, of the electric field that's vertical, that's gonna go through. So that would be E naught cosine theta, right? So this is the unpolarized light. Right? And I can, what did I call that? I sub intensity, I just called it I. Now, so if I just select one of these electric fields and I put it like that, only the component of it that is parallel to the transmission axis is going to go through. The rest is going to get absorbed. Now, what is the intensity of this light? It would be epsilon naught C over 2. You know, that's just the medium, speed of light in the medium divided by 2. And then I have to square that electric field, which will be E naught square theta, and I have to square that. But, there's a but. I only selected over here one particular electric field at one particular angle. There's another electric field at a slightly different angle, and a different angle, and a different angle, and a different angle, and a different angle, and so on, right? So, therefore, I need to average this. And what do you get when you take the average of the cosine square? So in other words, this is simply just epsilon naught C over 2 E naught squared, but then you have the cosine square theta, right? But I need to take because of these angles are, you know, because this angle is going to be different, so this is E naught cosine of theta, right? All of that electric field squared, right? I need to average over all the angles. And what is the average of the square of the cosine? 1/2. But what is this? Wasn't that the intensity of the incident light? Let's call it E sub 0. How about I call it E sub 0? And this one I'll call it E sub 1, like 1 after going through the first polarizer. But this over here is just I sub 0. You know, it's the intensity of the incident beam of light. So that means that the intensity of the transmitted beam through the linear polarizer, this is a linear polarizer, and the result is polarized light, right? Polarized vertically, the result is going to be 1/2 of the intensity of the light that was coming in. So this is true when you have unpolarized light coming in, going through a polarizer, only half the energy is going to go through to the other side. And the 1/2, why is it a half? Because the intensity of the light is proportional to the amplitude of the electric field squared. But if you take one of these, just run, you know, any one of these electric field amplitudes, right, the component of that electric field amplitude that's going to go through is the one that's parallel to the transmission axis. So theta is the angle that, you know, I decided to choose between a particular incident electric field and the one that goes through. So what goes through is E naught cosine theta. And so the intensity of this is going to be, well, proportional to this electric field squared, but I need to average over all the possible angles because I have various, all possible orientations over there. And the average of the cosine squared gives me the 1/2, so I get half the intensity. So for example, if the intensity of this light over here is, 10 watts, that's joules per second per meter squared. Well, the intensity of the light after going through this polarizer is going to be just 5 watts per meter squared, just 1/2. Yes? So that's that. Now, Malus's law, which was a long time ago, 1809, I think that guy was a captain in Napoleon's army, you know, the French dude. So Malus's law says the following. It says that, so there's a difference between Malus's law and this. And the difference is the following. So it's this over here, but Malus's law says the following. What if you have, as a, you know, you have your linear polarizer, and let's make the transmission axis vertical. Okay? And you send in light that's polarized already. That's different from this. Here, the incident beam of light was unpolarized. So I'm gonna, now imagine that I take this polarized light and I pass it through another polarizer. So it's coming in polarized. So now I have linearly polarized light coming in. And let's say it's polarized this way. With some amplitude, you know, oscillates up and like this, right? But notice that this is the transmission axis of this polarizer is vertical, but this electric field is oscillating at some angle to the transmission axis, which I'm going to call, I think it's called phi in the notes. I'll just call it phi, just to be consistent. So if I think of this electric field hitting this polarizer, right, what am I going to have? An electric field that's just, I just draw, you know, the field like this. And this angle is phi. Right? There's only one angle phi over here. The light is just coming in. All the light, you don't have all of these other angles because the light is not unpolarized. It's just polarized light at that particular angle. So what is the electric field that gets through? Well, the component that's going to get through the polarizer is this component, which is E naught cosine of phi. So what you get through is this component, which is E naught cosine of phi. Now, if the intensity of this light is I sub 0, that's the intensity of the incident light. What is the intensity of the light that goes through? Well, let's see. I can use that formula, epsilon naught C over 2, and then I need to square the electric field component that went through. Right? So this gives me epsilon naught C over 2 E naught squared, and then I have the cosine squared of phi. But what is this? That's the intensity of the incident light, correct? That's just the intensity of the light that reached this polarizer. So I'm going to get that. Now, I don't average over the angle phi because the electric field was only coming in at that angle. So that's just I don't do that. I mean, if, in other words, this is like constant. I mean, I could take the average if I wanted to, but what is the average of a constant? Just the constant itself. Right? So then this would be cosine of phi. And this is my Luce's law. That the intensity of the light that goes through the polarizer, when you have polarized light coming in, is equal to whatever the intensity was of the light coming in, multiplied by the cosine of the square of the angle that the electric field coming in makes with the transmission axis. What happens if that angle is 90 degrees? What happens if this electric field is oscillating horizontally?
There's nothing going vertical.
When it
so
oscillates
it's zero.
horizontally, it should be dark over there. You get no intensity because you get cosine of 90 is 0.
So Malus's law only applies to linearly polarized
Yes.
light, and then this one only applies to randomly
In
polarized.
both cases, you could say that in both cases, you should do it from here to there like that, and then take
Okay.
the average of the cosine. But because the cosine here is a constant, I mean the angle is a constant. Like if you take many exams, you get 80%, 80%, 80%. In all the exams, the average is going to be 80%.
Right.
So then you just have one angle over here because the input light was linearly polarized light.
Is that how the two planes and the computer thing?
Yeah, so in the demo, which I think most of you saw, I don't know if all of you saw it, but in the demo, you have, you place a polarizer like this, right? And what happens if the transmission axis of the second one is also vertical? So if light comes in, let's say you have light coming in, you know, the light source coming in is usually unpolarized, right? And the light from the room and so on, it comes in unpolarized. So you have some intensity over here coming in, right? So let's say I sub 0. What will be the intensity of the light over here? The electric field will just be like that. What will be the intensity of that?
I0.
Half of I sub 0, right? Because this is unpolarized and this is now polarized. So it'll be half of that. Now, what's the intensity of the light that's going to be over here? All of this is going to go through, right? So the intensity I2 is going to be I1, which is this, which is half of I0. Yes? Now, what happens if I begin to rotate this one? Then if I begin to rotate the second one, you know, some angle theta, suppose I call it theta, not phi. So what if we have the incoming light coming in like this, unpolarized? So this is unpolarized, right? That's what happens over here. I didn't say it, but this is unpolarized. Now this is polarized. And this is polarized. So you have unpolarized light coming in, right? The intensity is I sub 0, and then it goes to the first polarizer. It doesn't matter how I position that one, right? What you're gonna get over here is an electric field that points like that, and the intensity of that one, let's say I0 is incident, I1 after going through the first polarizer, and I'm gonna call I2 after going, the intensity of the light after going to the second polarizer. So this one is going to be 1/2 of what was coming in. Now, what if I set the second polarizer like this at some angle to the first polarizer, right? So this is now the transmission axis, and this angle is theta. So what will happen is that the electric field, right, coming in to this polarizer is like this, right? And the component that's going to go through is this one, which is in E cosine of theta. So then over here, the electric field is going to be like that. It'll be E cosine of theta. And what's the intensity associated with that? And that's one fixed angle, right? So this light is polarized, and this one is also polarized. So the intensity of this light is going to be what was coming in, which is I1 by Van Loos's law times the cosine square of this angle. And now I can take this, for example, and I can plug it in here so that I can express the intensity of the light going through the second polarizer in terms of what was incident to the first polarizer, and then this would be 1/2 I0 cosine square of theta. And what happens if you take this polarizer and you make that angle 90 degrees, so that the angle between this transmission axis and this transmission axis is 90 degrees? That's just making this angle 90 degrees, and the cosine of 90 is 0, so it gets blocked. And did you all see it, or do you want me to go get it? I'll go get it. Maybe some of you didn't see it.